sense. But I chose to talk about this because this is where more like current active research is happening right now compared to previous one. Although there are work going on previous one, but just by population in the physics community, more people are working on this for whatever reasons. And finally, I will talk about like relate this back to why we know about this concept. Why does everyone, the general public, know about this concept in the first place is in fiction, right? So because of that, I should probably give a spoiler warning just to be complete. I'm gonna talk about the third Spider-Man movie towards the end of this talk. Okay, so yes, I feel strange. This is the first time I give a spoiler warning in a physics talk, but just a heads up, right? But I'll be talking about physics most of the time anyway, starting with eternal inflation, right? The multiverses in cosmology. Okay, so everyone fine, right? Yeah. Okay, so eternal inflation, what is this about, right? This multiverse is gonna come into this story at some point, but in order to understand this story, we need to give a bit of context. So the story starts as a Big Bang Theory, right? So not the TV show, the theory. So the Big Bang Theory is a description of the evolution of our universe, right? So even here also, right, there's already one misconception I wish to get out of the way immediately. Like people like to say that the Big Bang Theory is the story of how the universe is created. That is a bit too much to claim, right? It's almost as if it's a religion kind of thing, you know, how the universe created, blah, blah, blah. But as a scientific theory, religion is not our business. What Big Bang Theory is, right, I would rather say that it's not how the universe is created, but it's this description of the evolution of our universe. What do I mean by that? It means that, you know, under this theory, like combining known knowledge of physics, like all this stuff here, we are able to describe a sequence of events in the past leading up to today. Okay, so that is precisely what Big Bang Theory is doing, right, as a scientific theory. Okay, so a sequence of events describing from the past until today, and what among the biggest idea is that the universe is much smaller in the past. So we have a sequence of events. Then the earliest event that we can have, that we can describe, the one in the front, is the earliest event, and people, you know, it's very tempting to say that this event that we are describing is the creation of the universe. But to be precise, right, it's just that using this present knowledge, we are able to describe until this stage only. Okay, it just means that we are not able to, we don't know what happens before that. Maybe the universe is really being created, or maybe there's a bunch of other stuff that is happening before that. We just don't know, right? So that's why, you know, I tend to be careful to distinguish the scientific Big Bang Theory, distinguish it separate from the story about how our universe is being created, right? So using this knowledge, we are not able to go earlier than that. And what is the knowledge that we're talking about is the general, the big pillars of physics: general relativity, standard model of particle physics. This is basically quantum field theory, QFT. And then you're gonna need some statistical mechanics to kind of like piece everything together as a single model, right? So what was the story? What was the sequence of events? This is a timeline of our universe, right? And this, you can kind of treat this as kind of like roughly like representing the size of our universe. So today our universe is really big, right? We know it's huge. But in the past, our universe is smaller. So what we do know since the days of Hubble is that our universe is expanding. And the first event that we are able to describe is this over here. Back then, the universe is really small, right? And at this stage, the size is very small. The density and pressure of all the substances within the universe is really high. The temperature is really high, right? And quantum effects are very strong here. So after that, there is this phenomena which I will discuss, inflation, right? It blows up the universe suddenly in size, and then after that, the substances and material in the universe is gradually cooling down, right? And as it cools down, the afterglow, the heat left over, is what we call the cosmic microwave background, which we can detect today. But as time goes on, all the substances cool down, they start to clump together under gravity. And as they clump together under gravity, the stars start to form. And stars start to collect together in galaxies. Galaxies start to collect together in galaxy clusters. And then eventually it evolves into what we observe today, right? We have Earth, we have our sun, solar system, everything. So this Big Bang theory is an extremely successful theory, right? Imagine if we can describe a lot of things pretty accurately from over the period of 13 billion years until today. So it is a very successful theory, but nevertheless, there are still some questions that the Big Bang theory cannot answer. So what are the questions? There are 3 problems I will very quickly run through. Okay, so the first problem is the flatness problem. And the idea is the following. So mass is something that causes gravity, right? So everyone knows that. And according to Einstein's theory of relativity, mass and gravity will curve the shape of the universe, right? So it will affect the shape of the universe. So it causes the curvature of space-time. And the more mass you have, the more curved it becomes. So therefore, if you think about all the collection of masses in the entire universe, all this entire collection of mass will affect the shape of the universe, right? So then we have 3 possible scenarios. This is based on solving Einstein's equation. If we have too little mass, if we have a lot of mass, if we have a lot of mass, a lot of stars and a lot of galaxies, too many galaxies, the gravity is too strong, it will just curve the universe into being a closed shape. So if we have very little mass, right, not enough galaxies, not enough stars, then the universe is open. And the intermediate, in-between, critical case between these two is the flat case. So if the universe have just the right amount of mass, right, not too much, not too little, it will affect the curvature such that it is not closed and it's not open, but is precisely exactly flat. So it is a very exact value that you must have. And the amount of substances in the universe is something we can observe, right? So people have done this observation, and it turns out that actually the universe is pretty close to being flat. So why, right? It's such a sensitive value to get a flat universe, and yet our universe is flat. Isn't it a weird coincidence? Or is there some reason why it should be this nice, precise value? Okay. Another problem that the Big Bang theory cannot explain is what is known as the horizon problem. But basically, if you think about it, this was the cosmic background radiation that we see in the background of the universe, right? So if we measure the radiation, so if any students here have taken thermodynamics class or statistical mechanics, you know that if you measure the wavelength of this radiation, we can actually determine the temperature of this background. And it turns out that the entire background has the same temperature, 2.725 Kelvin, right? It's very low, but the error and the standard deviation of this measurement is plus or minus like 0.01 or something like that. So basically, almost the entire universe is having the same temperature. That is very strange, you know. Why is it strange? Because how does something become the same temperature? If you think about it, right? If you take a hot metal and then take a piece of cold metal, and then if you touch the two metals together, then if you wait a while, then eventually they'll become the same temperature, right? So this is what we call, you know, having a thermal equilibrium state, right? So firstly, these must be in contact with each other, and also sufficient time must pass through so that it will settle down into a common temperature. Okay, so why is it strange for the universe? So if I look at this entire background, right, of the universe, right, just choose two regions. Let's say this region and this region, they both are at the same temperature. But if you think about it, right, if you actually measure the distance, the distance between the two is actually too far away. So it is so far that light still haven't reached from this point to this point yet. And nothing can travel faster than speed of light. So it is impossible for anything here to communicate with anything here. Okay, so if you can't communicate, then how can you reach thermal equilibrium, right? So the metal example, you need them to touch first, right? So you need to exchange information or exchange heat. You need to exchange something in order to make it the same temperature. But these causally disconnected regions, they still have the same temperature. Why? Okay, so this one is to illustrate the fact that, yeah, like ice and hot water, right? If you touch them, after a while, time passes through, let them exchange heat, then you can reach the same temperature, right? But apparently, the entire universe, even though they're so far away, is not. We are not at the same temperature. Okay, so that's the second problem. Then the third problem is the existence of magnetic monopoles. So what are magnetic monopoles? Well, let's start with electric charges first. For electric charges, right, we have a positive and negative charge, right? So this is why your batteries and all that have a positive and negative terminals. It's because of all these charges. Now, for electric charges, you can separate them, right? So you can have an isolated positive charge and you can have an isolated negative charge. For magnets, you have a north and south pole. But I think everyone knows that if you have a north and south pole, they are always together, right? If you want to cut a piece of magnet in half, you just get two magnets with two north and south poles. Okay, so you cannot isolate a north pole by itself, and you cannot isolate a south pole by itself using these magnets. Because so far we have not discovered a north pole alone or a south pole alone, right? Not like electric charges. But why? Okay, because according to theoretical physics, if you solve the quantum mechanics of electromagnetism, you actually need the existence of monopoles to explain other phenomena. For example, you need to explain the quantization of the electric charge and quantization of certain things if you assume the monopole exists, but we have not found one yet. So where are the monopoles in our universe? Okay, so in order to explain this problem, Alan Guth and Sato in the 1980s, they proposed a possible explanation. And the idea is very simple. So, I can't bring up my pen for some reason. Never mind. So they proposed the idea that sometime in the early universe, in the early times, the universe experienced a sudden accelerated expansion. Okay, so if this happens, they say, according to this theory, if this happens, then it will explain the three problems. So I'm looking at the time now. So yeah, so I shall not spend too much time to explain why. But maybe the most interesting one I would say is this. Right? Why does the entire background have the same temperature? Is because at the beginning, the universe, we know it's quite small, right? So maybe when it's very small, it has enough time to interact and exchange heat and become the same temperature, right? And then after that, this sudden expansion blows up the size of the universe. It becomes really large, and then they become very separated. And that will explain why the background has the same radiation, same temperature everywhere. Okay, so that is one possible explanation. But of course, this is just to say that if the accelerated expansion happened, but why would such an acceleration happen? So you need to give a mechanism, right? So I think until now, it is still not yet a solved problem. We don't know why, if this happens, why should it happen? There are many people who propose many different mechanisms. See all these words all here. Right? All these are like different proposals, different ideas you can work on. And this literature is huge. There's a lot of people working on it with no clear answers yet. But what we want to focus on is, of course, for today is the idea of multiverse, right? So one of them, a few of these related theories will imply the existence of multiverse. But what does the multiverse here mean? So the technical term, if you want to search literature, right, is eternal inflation. And one of the earliest authors was by Steinhardt and Vilenkin, also around the 80s. The idea is that the eternal inflation happens when suppose our universe is initially in the false vacuum state. Okay, so what do I mean when I say false vacuum? There's a lot of this technical terminology in physics, but don't worry, right? So all we need to know is vacuum is something that we kind of know, right? Vacuum means nothing, right? So no air is when space you suck all the air out of some region, then its vacuum means you've got nothing inside, right? It's just space. So space will have its own energy, right? And usually physicists assume that the state of vacuum is the lowest energy state, okay? But it's not guaranteed to be true. Maybe there is another situation where there's nothing, but the energy of this state is slightly higher. It depends on the details of the space-time, which I'm skipping. So maybe there are two energy levels of vacuum, maybe more, okay? So if one of them is at a higher energy level, another thing we always know from physics that it always happens is that systems in higher energy eventually will relax into a lower energy state. Okay, so the idea is that maybe in the early universe, it actually is being created in a vacuum of the higher energy level, right? And then by random quantum fluctuations, certain points will decay into a lower energy state. And when it becomes a lower energy state, then it will be like our vacuum that we are experiencing today, which is our expanding universe. Okay? But because this transition, because it's quantum mechanics, transition is random. So it happens at random points. We don't know, right? Quantum fluctuations. So maybe at one point, a transition randomly happens, so it will decay into a true vacuum, the really low energy level. And this part of space becomes the early universe, and it slowly expands, right? So it expands. So let's say this is our universe that we are living in. I'm drawing time here. So as time goes on, our universe gets larger and larger. Okay. But as I said, the transition is random. So maybe randomly at some other point, this part will decay into a true vacuum also. Then this part will become its own universe, then it will expand. Then randomly at some other point will decay and then it will become another true vacuum, and this true vacuum will also expand. So this transition from false to true vacuum is the mechanism that causes the inflation that Guth and Sato wanted. So that will explain the unsolved problems in Big Bang theory. And if this happens, then we kind of have the complete picture. But if you want this to happen, and because of all these random fluctuations, then the implication is that other points will transition and other points will have its own universe. So we can imagine every universe is being created as a bubble, right? Because it's random, so everything at random points, a different universe will bubble out of the false vacuum, right? So like this, and imagine like a boiling water, so bubbling out everywhere, right? So that is the idea of the multiverse here, right? So that was the eternal inflation that started from the 80s, right? So artist's conception about this is you can kind of imagine like, okay, this is one of our bubble universe, transition into true vacuum, and then it expands, another one pops out, it expands, another one expands, and the space between them is the false vacuum state, right, which haven't yet been, we're still in a false vacuum. So that is one potential candidate for an idea of multiverse. But what are the other consequences of this theory? So maybe there's gonna be some slightly disappointing news. Is that the consequence is the following? So if you work out the theory, right? If you work out the math and all that, you will find that each bubble, each pocket universe will have slightly different values of physical constants. So maybe in another universe, the speed of light is slightly higher. Maybe gravity is slightly weaker, right? Maybe h bar is slightly larger, and so on and so forth. Maybe the electron has a higher charge. And because of this, right, maybe life cannot exist in the other universe. So this is what is called under, there's a branch of like partially a philosophical discussion about the anthropic principle, which I'm oversimplifying the entropic principle, so people will scold me, but the idea to make it simple is that life will evolve in the bubble that has the correct values of these constants to support life. If you think about it, right, it kind of makes sense, because what is life, right? Why are we alive? Our bodies. We have our cells, right? We are processing oxygen. We have DNA, right? What is a DNA? DNA is just molecules. They are bonded together by the Coulomb force. So if the electron charge is too strong, then the molecule will collapse. Or if H bar is too small, the atom is classical, then it will be, the orbit will decay through radiation. So if all these values are wrong, then DNA cannot even exist in the other universe. So how can life exist, right? So yeah, so other universes may not support life, and even if we can travel to another universe, we will die because our bodies will just decay and collapse. So maybe that is a slightly disappointing news for the cosmological multiverse. Yeah. So does anyone have any questions so far? Yeah, I'm just occasionally checking just to see if I'm disconnected, but I'm not. Okay, so if everyone is okay, then we go to a different story of multiverse, which comes in the story of quantum parallel universes. So I think, right, this would probably be closer version to what the Marvel universe multiverse thing. So you have branching universes in Doctor Strange and Loki and all that. Yeah, so again, right, in order to understand this story, I need to give a bit of context. And I'm going to talk a little bit about quantum mechanics. And I see in the audience there was a few of my QM students, right? They will feel a bit bored because I'm telling them the same thing again here. This is the two-slit experiment, right? But so yes, let's talk about it a little bit. Okay, so yeah, so even for the USM students who are taking quantum mechanics, you've probably seen this before, right? So the idea is the differences between waves and wave-particle duality. Particles and wave are two different things, right? So those of you who are not physics people, particle and wave are just from the words, right? Particle are just like, things moving around. Wave is like water wave, okay? So those are two different things. We can do an experiment to distinguish between these two different things. Let's start with particles first. So if we do an experiment with particles, let's say bullets, right? So if I have a gun, and then this is a wall, right? And then I cut out two holes in the wall. And then I take the gun and I let it shoot randomly. Okay, so if I shoot it randomly, then of course most of it will hit the wall and get stuck. But if it passes through the open gap here, then it can travel through, right? Then it will hit the side. So these are bullet holes. So if I travel through the second slit, it will pass through and get the second set of bullet holes here. Right? So if you shoot the gun randomly, then you get this stuff. Okay, so this is what happens with particles. And of course, if you block one side, then all the bullets will travel to the left side. If you block this side, all the bullets will travel to the right side. Right? This one, yeah, nothing special. Everyone knows this, right? Everyone knows particles. But if you do the same experiment with waves, you get different picture here. Because if I take a wave, right, lights are wave. So if I shine the light, right, if I shine the light source, then light will emerge from these two slits. And what you see on the other side is the alternating bright, dark, bright, dark, bright, dark, so on and so forth, right? It's not just two, right? Bullets, you only have two. But if you do it with waves, you have, right, bright, 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 right? A sequence of fringes. So the reason this happens is because for waves, you have interference phenomena. So wave from the left slit can interfere with the waves from the right slit. Okay? So yeah, so this same thing, if you block one slit, then you get one band, you block second slit, you get another band. Of course, I'm ignoring the single slit diffraction. That's not related to our story today. So what if we do these experiments with electrons? So if we electrons, right? Electrons, we kind of learn about electrons in high school as particles, right? We do know its mass, we know its charge. It's particles that they can travel around. So we expect to see bullet holes, right? If you shoot a bunch of electrons and then you hit it in a screen, right? Is this true? Now, this experiment can actually be done. In fact, in most universities, you can find such an experiment there, and you can actually do the experiment and you find that you get the wave pattern. But the wave pattern with bullet holes, that's the funny thing, right? Because electrons at the end of the day, yeah, you detect them as points. So each of the electrons are hitting here with bullet holes here and here and here. But for some reason, even though there are bullet holes, they follow the interference pattern as if they are waves. So what's going on here, right? So this is very strange. How does an electron travel that all of them are here, 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 and almost none of them are in the gap in between, right? It contradicts to what we expect from Newton's laws, because Newton's laws, you can solve like F equals to ma, travel, and then, right, collision and stuff. So this one, we don't expect this to happen, so we need to investigate and find out. Right? We can ask some basic questions. Let's take one bullet hole. This one on the right. So this electron, how does it arrive here? Did it travel through the left slit or did it travel to the right? Right? Which slit does it pass through? Right? So we can do another experiment to find out. Okay? So let's say I attach another slit checker so that every electron that passes through, we record the electron passes through the left slit or the right slit. Right? So we take attendance of the left and right slit for everyone. And when you actually do the experiment, you get this. So imagine, right, in the early days, people actually doing the experiment, they'll be like very frustrated, like why the electron change their mind when you do this, okay? So it turns out that if you observe which slit it passed through, then it comes back to becoming a particle, like a bullet, the same result that you get as if it's a bullet. But if you do not observe it, you get this fringe pattern. Okay, so this is a manifestation of a wave-particle duality, right? So what is a particle? What is a wave? Like I said, a particle for the non-physics people is exactly what you expect, just a point moving around like this. A wave is a phenomena that occurs everywhere, right? So a particle is at one point, at one place at a time. A wave is like spread out everywhere. And it turns out that whether an electron behaves like a particle or behaving like a wave, like just now, it depends on whether or not we observe it. So observing the particle influences the experimental outcome, right? And like checking the trajectory, checking which slit you can only figure it out when you make an observation. But if you do not make an observation, then it's like a wave. Only when it's a wave, you can do the interference. This is why you get the interference pattern. Okay, but yeah, so the observation will force it into one of the outcomes. And another feature of quantum mechanics is you cannot predict which outcome you will get. Okay, so it's random. Let me explain with another experiment. So let's say I have a particle. Let's say just two outcomes, right? So my students will know the spin. Okay. So let's say a particle, for the non-physics people, just imagine a particle can be pointing up or a particle can be pointing down, right? So maybe you can imagine like little arrows over here. And if you do not observe it, if you put it in a box, you do not know what is the state of the particle. And only by opening the box, technically speaking, you're making an observation, right? You act with a Hermitian operator, then you can identify what is the probability of getting outcome 1, how to get outcome 2. So before you observe, you don't know. And that is the problem here. What do we mean by not knowing, right? So this comes in by interpreting the quantum mechanics. This is an issue about the interpretation of quantum mechanics. So this question becomes even more ridiculous when we do the Schrödinger cat experiment, right? Because why? Let's go back a little bit, right? Taking this example, for this electron, before you observe it, it's like a wave, right? You don't know it's everywhere, right? So which state it passed through, you don't know, right? It's in this superposition state. Only when you observe it, you can like narrow it down to becoming a point. before you observe it, it's a wave, it's everywhere. So if you, before you observe the spin, you don't know what is the spin is everywhere, it's either both up or down. Okay? This is ridiculous if you imagine a cat inside the box, right? So if you put a cat in a box and then let's say there's a poison gas inside the box, and this poison mechanism is only triggered when the particle is being in spin down. So if I put a particle, unknown particle in the box and a cat inside with the poison inside, and I set it up such that the poison gas is released if when the spin is pointing down, that it will kill the cat. If the spin is pointing up, the cat is safe, is alive. Okay? So the idea is that, yes, like what I said just now, if I do not observe it, it's like a wave. Then in terms of that electron, it's like a wave, is both states are happening at the same time. Then what is the cat doing before you open the box, right? So we know that if you make an observation, if you open the box, yes, maybe you'll find the cat alive, maybe you'll find the cat dead, right? But you only know after you open it. But before you open it, what's the cat doing, right? So that comes to a philosophical question of how do we interpret the quantum states. So this is kind of like one of the open questions in quantum mechanics, right? A lot of ideas and proposals, and I think, you know, if you ask different physicists, they have different ideas. I mentioned 3 different interpretations. The first one is the Copenhagen interpretation, probably among the most popular, but also the one that Albert Einstein did not like, is that the states have no objective existence prior to observation. That means the state does not exist before you open a box. So the cat story is the cat does not exist before you open the box, right? So only the observation creates the objective existence. It is a very radical statement, right? It's like you need an observer for something to exist. Okay, so it's very radical, but they come to this interpretation because from quantum mechanics, you cannot access what happens before you open the box. So you might as well treat it as if it doesn't exist. The second interpretation is what we call the hidden variable. This one, right, is, I would say, the most reasonable interpretation, the less radical, the most conservative. It says that, yeah, actually, the cat is actually already dead or already alive in the box. We just don't know it. And we don't know it because the equations of quantum mechanics is not powerful enough to solve the problem. Okay, so yeah, the equations are not enough to tell, so that's why we call it a hidden variable. Okay, but the problem is we can actually test this assumption, and this is known as Bell's theorem, and Alan Aspect in the 80s have done experiment. It actually rules out this hidden variable. So hidden variable idea turns out to be not applicable here. Then the other one is what we are here to talk about, the many worlds interpretation. So the idea is, well, it's slightly more reasonable than Copenhagen, more radical than hidden variable. Why is it more reasonable? Well, Copenhagen says that the cat doesn't exist before you open it, right? In some simplified way of talking. This interpretation says that the cat exists, but in these 2 universes, right? There is one universe where the cat is dead. There is another universe where the cat is alive. And us opening the box is us finding out which universe we are in together. Okay? So if you open the box and find a dead cat, that means there's another universe parallel to us, that a copy of myself opening the box and finding an alive cat. Right? So this is what is known as the many worlds interpretation, or, you know, in our language is the multiverse. So this was proposed by Hugh Everett in his Ph.D. thesis in 1957. So his thesis is available online. You can download and read it if you want. He would explain all this in detail. And unrelated to our talk, but I still find it interesting to note that Everett's son is also very famous. He's the lead singer of Eels. So you can find his music in Spotify and everything. But many worlds, right? So why did Everett propose the many worlds? In some sense, it's because he is trying to be more reasonable than Copenhagen. Copenhagen is, even me too, I feel it's a bit extreme. If you do not observe it, then the reality does not exist, right? It's a bit, hard to accept. But here is slightly less radical in the sense that the reality exists. It's just that there are two versions everywhere. Okay, so why is it more reasonable? So it's a bit hard for me to explain, but if you actually go through the math, right, you feel like it's even more reasonable because, in math, so in the Copenhagen interpretation, right, the math, right, let's say you have the state. If you're not familiar with the math, it doesn't matter. But the idea of math is, the idea of Copenhagen interpretation is, before observing, right, you do have an equation that represents what is the quantum system inside the box, right? You do have an equation, but even when you have the equation, the Copenhagen says that it doesn't exist. Only when you observe it, then either one or the other exists. So in mathematical calculations, why do you say that if you go from one step, this part doesn't exist, but the next step, it exists, right? So in that sense, the multiverse interpretation is kind of more reasonable, right? You have an equation that represents the quantum state inside the box, the cat, and it says that it exists. It's just there are two universes, one in which the cat is dead, another universe is the cat is alive. And in going to the next line, right, then you're not really making a big jump in your mathematical calculation. So on here you get universe 1, on here you get universe 2, right? So yeah, so in that sense, hopefully, it's a bit more reasonable. But maybe what people would want to know is that if the multiverse theory is true, can we communicate to a different universe? And it turns out that it depends on the details of the Schrödinger equation. So there is a paper, people have actually worked this out, that if the equation has a slight non-linear term, then this paper kind of gives you a procedure to send signals from one universe to another. But Schrödinger equation, if it's non-linear, okay? So the Schrödinger equation that is being taught in class is the linear version. So and maybe there is a regime where Schrödinger equation becomes non-linear, then it's true. But to the linear approximation, you can't do it. Okay, so yeah, so this was the second part of my story, right? The quantum multiverse. Then, okay, so I will try to spend about 7 minutes to talk about this last thing, the holographic universe. So what do we mean by holographic universe? If you Google, right, you probably see articles that claim that physicists claim that we are actually living in a hologram. What do I mean by hologram? So this is a famous hologram, right, from Star Wars, the first Star Wars movie where Luke Skywalker found R2-D2, and inside this robot there's a recording, and this recording is projected in 3D space. So this is what we mean by hologram. Hologram is an image, but a three-dimensional image, meaning that you can look left, look right, you walk around, you have all the shape, you can see everything, right? So you can see in all directions. This is a hologram. And the interesting thing about hologram, right, is it's a real technology, not just Star Wars stuff, but it's a real technology, and it's actually a 3D image, like I said, but you store it in a two-dimensional film. So we do have this since the 1980s. So it's like literally like a photographic film, right? So it's flat. And then if you shine a laser light through the film, you can project a three-dimensional picture. So the idea of the hologram is, even though you get something three-dimensional, but actually everything is stored inside a two-dimensional surface. So it's one dimension less, okay? So 3D information is being stored in a two-dimensional medium. So why do we start to have this holographic theory is, the story starts from the concept of entropy. So entropy is a big topic, but for today's purposes, entropy is just measuring a certain situation. What are we measuring is how messy or how organized is a system. So if I have a system, right, and have particles, and if everything arranged nicely, this is something I would call a low entropy state. Okay. If I have something that is all mixed up and very messy, random, so this is a high entropy state. Okay. And then also, right, the value of this entropy in this state depends on the volume of the system. So if the box is twice as large, then the entropy can be double. Okay. So if you think about it, entropy has something to do with information. Entropy tells us how something is being organized, right? Or something is being distributed. So entropy is very closely related to the concept of information, right? It tells us how a system is being distributed. So the larger the entropy is, the more ways, the more information you can store into a system. This is why entropy scales with volume, right? So the bigger something is, the more information you can store it inside, right? Right? The larger the book, the more words you have inside. So that is the basic idea of entropy. Let me skip this. But what I do want to share here is that you can actually compute the entropy of a black hole, but it was a surprise at the time. So the story starts, I'll start this story here. So around the 70s, people who are studying relativity know about black holes already. So at that time, people are studying how the black holes behave. And in this paper published by these three authors, they summarize the behavior of the black holes in 4 basic general laws. They call it the 4 laws of black hole mechanics. So this is Bardeen, Brandon Carter, and Stephen Hawking, right? So I believe Stephen Hawking is the most popular here. So everyone might have seen this before, right? So there are 4 laws of black hole mechanics, and the surprise here is if you write the laws side by side with the 4 laws of thermodynamics, they look the same, even though they are talking about different things, right? One is black holes, right? Gravity, mass, how things fall into a black hole and cannot escape. So black holes. Then thermodynamics is the kind of things that you learn in your thermodynamics class, even engineering students would know, right? Like ideal gas, temperature, heat flow, and stuff. So those are like 2 very different things, but if you write the equations, they kind of look the same. If, on this side, black hole, this is surface gravity, and for thermodynamics, it's temperature, okay? Then for second law in thermodynamics, you have learned about the second law. So the second law says that entropy can never decrease, it can only increase. For black hole, I have the same equation, but for area. But area, that even makes sense, right? The size of the black hole can only increase because anything that falls into the black hole can never come out anymore. So stuff going into a black hole, it becomes larger. Then more stuff get more larger. So black hole can only increase, it can never decrease in size. So are they the same, or is it just a coincidence? So Hawking continues to work on it, and along with Bekenstein, and eventually they realized that it's no coincidence because black hole can be treated as a thermodynamic system. In fact, they derive a more precise form. It's not just the area, but area divided by 4g, and with I think other constants set to 1. But they found a precise formula relating the area of the black hole to the entropy. But here's the funny thing, right? Entropy, just now when I said entropy depends on the volume, but here entropy of a black hole depends on its area. Why? One-dimensional lower. Okay, so more clues start to come in when people started working on other theories, for example, string theory. Eventually, they kind of like getting more and more clues, that somehow all the calculation about information is related to area rather than volume. So it kind of gives us the feeling of hologram here, like a 3-dimensional piece is somehow encoded in a flat two-dimensional area, right? So the Hooft and Susskind, they propose the holographic principle, which kind of states what I've been talking about. Information about things in a volume is actually can be encoded on the boundary, which is 2 dimensions or 1 dimension less. Okay, so I'm leading up to, I chose this topic and leading up to this because it is an active area of research today. You might see it under the name of the ADS-CFT correspondence, right? So yeah, so Lai and the rest of you were telling me you're interested in theoretical physics, right? So some of my students are too. And if you're interested, then this is probably something to look at. So what is the ADS-CFT correspondence? It is a concrete example of a holographic principle. And specifically, ADS-CFT was a conjecture given in a paper by Maldacena. So Juan Maldacena, he's here. And what do the words mean? So ADS means anti-de Sitter space. It is a gravitational system, let's say in d plus 1 dimension. So let's say 3 dimensions, right? So 3-dimension gravity. So it's kind of similar to our universe, but anti-de Sitter is not the same as our universe because our universe has a positive cosmological constant, but anti-de Sitter has negative, right? So doesn't matter what cosmological constant means. The main point is they are different, but it is still a gravitational system. It is a universe described by theory of Einstein's gravity. And then the CFT is conformal field theory. It's just quantum theory, nothing to do with gravity, but in 1 lower dimensions. Okay, so the idea is, so this ADS-CFT is the idea that a gravitational system in 3D can be encoded by a quantum system in 2D. That is even more amazing, right? The hologram itself is already surprising, but even more surprising is that gravity is encoded by quantum theory that has no gravity here, right? So this part has no quantum theory, it's just gravity, but it's encoded by this part, which is just quantum, no gravity. There are 2 different theories, but they are encoding each other. So that is why it is very surprising, but also definitely very interesting, and also why many people are working on it. So, so it's very hard to visualize this. You know, in a public talk, I know not everyone is physics, and please do ask questions if I say something that you didn't understand, right? Sometimes I went too fast. But I try to visualize something. It's very hard, but here, this is the best picture usually people use, is this picture. So let's say this picture is, this space is some universe, right? Anti-de Sitter universe. And it's in 3 dimensions. So it turns out that whatever that happens inside this universe, okay, physical phenomena that is happening here, can be encoded in a quantum theory on the boundary, which is 2 dimensions, right, or D in general. So so that is the encoding, and that is the holographic principle. Then, of course, you guys might be wondering, so, you know, back to the original question, are we actually a flat 2-dimensional hologram, even though we are 3 dimensions? And my simple answer is, I don't know, maybe not, right? And what does it mean if we are holograms? Because whether or not our lives can be encoded in a 2-dimensional piece, we still need to live our lives as if we are in 3 dimensions, right? We need to do all these 3-dimensional things. So this question doesn't really make sense, at least to me. But one of the spin-off research that we have from ADS-CFT is that it is a valuable tool that you can use it to other areas. Because, right, because like I said, a gravitational theory is related to a quantum theory. And then these are 2 different areas. So now we have a very useful method, because people in quantum mechanics, usually, you know, equations in quantum theory, it's very difficult to solve. But using this ADS-CFT, you can turn this into a gravitational problem, and then gravity people develop their own set of methods to solve the problem. And once you solve the problem, then you bring it back to quantum mechanics, you get the answer over here. Okay, So which is a good thing because when at the start of the talk, one of the students said that you're interested in condensed matter physics, right? This is where this kind of thing comes in. So in condensed matter theory, like one of the things that you want to measure is maybe a superconductor, and you want to measure the electrical conductivity. That in condensed matter theory, these equations are very hard to solve. Okay. At best, people do experiments. So they measure the conductivity and the current flow of some substance. But if you use ADS-CFT, right, you turn this into a gravitational problem. So this is just, Einstein's equation with ADS. And then you solve the equation, then you can actually get the graph that looks pretty close to the experimental result. That is pretty amazing, right? So a gravitational theory, you can kind of derive the same quantities that you could have get in the quantum theory. And sometimes quantum theory is a very hard to solve problem. But getting this graph is not difficult in gravity. Okay, so yeah. So I think I'm a bit short of time. There's another interesting thing with another concept. Rather than one lower dimension, this idea is we are in a one higher dimension. So this is the Randall syndrome braneworlds. The original idea was proposed by Lisa Randall and Raman syndrome, but I think I'm a bit short of time. So maybe if you want, I can come back to this later. But the idea is, we are in a higher dimension, so our universe could be just one slice, and inside a 5-dimensional space, and in another side, maybe there's another slice having another universe. Okay, so yeah, so going back to why do we always think about multiverse? It's usually what we see in movies, right? So in movies, why do multiverse always come up? And I would say that in fiction, right, storytelling, it is an art. It is almost never about physics or science or whatever, but it is usually what writers call a storytelling device, right? It is natural for these stories to come up because it is kind of like a common emotion that we feel all the time. Like we always, throughout life, we always ask ourselves, what if I make a different decision, right? What if I do something different, So what if I didn't do a career in physics, right? Then, this Everett parallel universe theory might suggest that if I make a different decision, I branch out to a different universe. So maybe, there's another universe where I did not do this job. Then I don't know, you might be wondering, what would your life be like if you've done something different, right? So maybe my other me is doing something. Maybe he's dead, or maybe he's rich, or maybe he's just drunk, or whatever, right? So there's many of these stories around here, and that is kind of like what you use as a tool to explore what are the emotional consequences of making different decisions. You kind of learn life lessons out of going through these types of stories. And then another thing is that it is another storytelling device to have. Why do people have multiverses? If you watch things like Narnia or Stranger Things and things like that, is characters that come from our world, like a normal life, right? Just like our country and whatever things, but they somehow end up in a fantasy land with monsters and everything. So that is why multiverse is being brought. It is one method to bring. What we want is a relatable character, right? And relatable character is something that comes from our world, that goes to school, that things like that. And then you want to transport this relatable character to another place with monsters and things. So maybe the writer wants to tell a story with monsters and stuff, but of course, in writing, your characters must be relatable. You need to understand what a person is feeling, and it is easier to understand a person from your own life, similar to yours, what they are feeling, rather than some warrior knight person that comes from a different life, right? So that is why you have these things, these kind of stories. And then another thing is, in a bit more, is simpler reason or more cynical reason is just money, right? So this is Marvel. We have this all these all these multiverses coming together, and because it's simply just a consolidation of intellectual property, right? And the Spider-Man case is an interesting story because in the earlier Spider-Man, the rights of that story is owned by a different company, Sony. So these two actors were playing Spider-Man when they are still owned by Sony. And then over time, they got their own fan base and things. And then now Marvel share the rights with Sony right now. And then this new actor come in. So you get many fan base from all everywhere. So of course, it would be obviously interesting and fun for everyone to watch a movie where everyone is together at the same time, right? So if you talk about mass market appeal, that was the most obvious profitable decision. And how do you bring all this together? We talk about, that's why the multiverse storytelling is being used to explain their existence here. Right, so yeah, so that was the only spoiler warning. That it's not much of a spoiler, but that's the reason why I put the thing at the beginning of the slide. Yeah, okay, so I think that's all from me today. So thank you everyone for coming and spending the time today. So I guess I shall turn over to questions.
Okay, thank you, Dr. Lim, for sharing his invaluable knowledge. This is amazing, and this amazing talk, amazing. Yeah, it's sound like transform the complicated knowledge or complicated terms into popularized, so we can know more about the physics knowledge. Okay, in terms of this. Okay, so now let us proceed to the Q&A session. Yeah, Q&A session. So in the chat box question, we put it in the Padlet. Okay, so to make it clearer, so okay, so I should start from the left side. Okay, left side. Yes. Okay, I read out the question and okay. So from the left side, braneworld, about the braneworlds and interstellar. Okay. It's a concept. It's a concept of the movie in the Interstellar, based on the brainwash theory. Because during the middle part of the movie, when Matthew, sorry for my pronunciation, falls into the black hole and sees things of the past.
Oh, okay, so I answer now. Yeah, what Matthew McConaughey or something. His name in the movie is Cooper, right? So kind of yes. Brainworld is slightly yes in the sense that Brainworld is a 5-dimensional theory, and in the movie they did not explain any details, but they say something about 5 dimensions. But this part, right, is so Interstellar is famous for like bringing all the real physics concepts into the movie, but this particular part is the least physics of it. So simple answer is yes and no. Brainworld theory has nothing to do with time travel. Not that I know of. Like even if there's some closed timeline curves, you can't really do the interstellar scene exactly. But yes, a bit no. The answer, yeah. Hopefully that makes sense to you.
Okay, so how we can answer the question? Yeah, so it's a question from the right side. Okay. The beginning say that doesn't a black hole decrease in size through the Hawking radiation? Because Doctor mentioned that black hole second law, the radiation should be increased, but the Hawking radiation said that black hole decrease in size. So it's
correct. Yes, I was kind of ignoring Hawking radiation, but you're right. It would decrease in size in Hawking radiation, but so that is included in the Bekenstein and Hawking's paper, but the total entropy is still increasing. So if you take the area of the black hole is entropy and is decreasing, yes, but if you count the entropy of the radiation, right? So S1 plus S2, and then you add up the two terms, it will be increasing in total. So yes, I'm just like skipping. I'm skipping through the Hawking radiation, but the entropy is still increasing.
Okay. Okay, so the question from the downside. Is it possible that the Schrodinger equation is non-linear in other universe, but only linear in our universe? If so, how communication can be achieved in between this universe, which is a mixed universe with a linear Schrodinger equation, and other universe with non-linear Schrodinger equation?
Okay, that's an interesting question. So yes, but in order to even like make conclusions about parallel universe, right, we need to use one Schrodinger equation to say what happens in all the other universe, right? So at the theory level, right? So at describing what the parallel universe does. So if you want to say that Schrodinger equation actually has a nonlinear term, we must kind of say that every universe must follow the same Schrodinger equation. So in that sense, either everyone has the same Schrodinger equation or not. But of course, you can kind of like, I know what you're thinking, right? We can kind of like have fun with the eternal inflation theory, where the physical constants, converge into different values in different universes. So why not the fundamental laws of physics, among which the Schrodinger equation? So you can kind of explore that, but we need to try to kind of like think of a way to have a consistent description from one to the other. But that's a very interesting thing to explore.
Okay. Okay, so next question. Okay, this is from Lowen Song. Okay, it's a bit long. Okay. Hi doctor, I have a question or rather a thought about the theory of eternal inflection. If it is true that at a different spatial point and a different time, a bubble universe can be created, then can we assume that at one point in space-time, events from, say, universe A and events from universe B can be causally connected, and the manifold is somehow connected in a literal sense? So I continue to read. I just thought it would be interesting because suddenly your manifold is stitched together, and when you travel from one point crossing to the other bubble universe, suddenly your speed of light could be different. Then maybe Einstein equivalent principle will be wrong because of the laws of physics are no longer the same on a flat space-time the moment you stay on the boundary.
Yes. So again, because in order to have a theory at all, right, we need to have a single theory to describe the entire thing, which is the Vilenkin and Steinhardt theory of the eternal inflation. So it will not imply the equivalence principle is wrong, because the equivalence principle is the same everywhere, just that for different speeds of light, right? So in practice, it's like I think you probably end up rescaling quantities, but at the end of the day, time-like vectors are always time-like, null vectors are always null. And then another issue also, right, about crossing the boundary to a different universe. It might be possible, but the thing I kind of like jumped right through and didn't spend time explaining is that the universe is expanding. Okay, so if you use the same description for all the multiverse, like the same Einstein equation, then all the new universe bubbling up are also expanding. And the space between the universes, the false vacuum, is also expanding. And I think because of this expansion, right, and because we are limited by our own everyone's speed of light across different universes, it might not be possible to jump from to travel from one universe to another. So, but that might be one way to prevent us from traveling there.
Okay. Hope that okay. So next question. Okay. It's a question. Okay. Hi, doctor. How does gravity and quantum system encode each other? Are not the two theories incompatible?
Incompatible.
Thank you.
Uh, yes, they are incompatible. So the reason why quantum theory and gravitational theory are incompatible is because we cannot have a quantum theory of gravity, right? So so we cannot quantize gravity. Say so for for gravitational phenomena, we cannot find its quantum effects. We don't know how to do it, but if you don't make it quantum, right, just like Einstein's theory or even Newton, it's perfectly fine. It works perfectly well. So the surprise of the ADS-CFT correspondence is that in the regime, the classical regime, we call it, right? Before you go quantum, all this information that is happening here is encoded in the quantum theory. It doesn't mean that we are having a quantum gravity theory. Does that okay? So it just means that a classical gravity is encoding something about quantum mechanics that has no gravity. So they encode each other, but if you want quantum gravity, you need gravity itself to be already quantum. Right? So you can't make it quantum. You have this classical theory, but ADS-CFT says that you can encode a quantum theory with no gravity, right? So so that means the two theories, they are incompatible, but they are valid in their own regime, in their own domain. That is the encoding, right? But the quantum gravity problem is we want to expand the domain for gravity to include quantum effects. That one still haven't been done yet. That one is still a difficult problem.
Okay. Okay. So next question. Boundaries. Hyperframe. I wonder if ideas in complex analysis like Cauchy integral formula that states that a function defined on a disk is determined, or rather have critical information encoded on the boundary of that disk, is related to the boundary and breakholding you described in your talk.
Not directly. So yeah, so the Cauchy integral, so for those who haven't taken complex analysis, right, you can the closed loop integral or on the domain, it's determined purely from the singularities that you enclose, right? So that kind of thing. So I would say no, because this one is just stuff related to complex numbers and that kind of thing. And it's also not really related to one dimension. Cauchy integral, you can do it in, so 2 dimensions, or maybe there are generalizations. Yeah, there are, but it's different thing. But I do want to say that, calculations in the ADS-CFT does use Cauchy integrals and things. Just that it's not, the boundary in the Cauchy integral is not the boundary in the quantum theory. And another thing I want to mention, because I find it like very interesting, is like complex analysis, use complex number, right? And you can do complex analysis on space-time itself. And the most interesting fact I find is that if you make time as a complex number, right? Time is just a number, but if you let t, generalize t to be z, a complex number, then the imaginary direction somehow becomes like a temperature, right? So I mentioned temperature, and then entropy of the black hole comes in again. And so all these issues are, is big rotation. And also yet another aspect of ADS-CFT, a lot of people are working on it. But I think, yeah, this is off in a tangent. So, yeah.
Okay. Okay. So yeah. Will it be possible the definition of life is different in other universe, which what we define life here may be a lot in another universe, but a lot can be a life in the other universe by John Hao, Lockman.
Oh, okay. Yeah. Yeah, I guess that depends on how you define life, right? And I think there are people might disagree on exactly how you define life. So yes, like a rock can be alive in not just another universe. Like maybe we are like aliens, right? Aliens are like totally different from us. So that could happen too. So it's not a problem, not just multiverse. We already have kind of the definition of life here. So I think, a simple way to define life is a mechanism that can self-replicate. You don't need DNA, you don't need carbon, but other people prefer to define life through carbon. But then, yes, it's not a clear-cut definition of how you say what is life. Maybe a collection of gas, that can have electric signals travel through one another, right? It's just, they have no body. It's just some gas with electrical signals. Maybe it can, because maybe it can become like a brain. Then maybe it can start to think, right? Do you call that life? So I don't know. But that concept, I think, is in a book written by Fred Hoyle. It is a novel, and it is interesting to explore, like, what is life? So I don't know whether that makes sense.
So here's a book recommendation from Doctor. Okay, so hi Doctor. We know that you are an expert in the field of GR or quantum theory. So can I ask for your recommendation for us to study quantum theory and also GR in terms of introducing and also advanced?
Okay. So quantum theory, I think there's a lot of very good books, and if I recommend, I would recommend my favorite ones, which I'm using with in my course. The good introduction probably is the Griffiths QM book, and then another one would be Leboff. Feynman lectures are, some chapters are good, some chapters are not. And then for graduate level, I think Shankar, Sakurai, and then quantum field theory, Ashok Das, that is a very good book. So and then for relativity, a good book will be Schutz. So Schcutz, Schutz. For usually it's an undergraduate fourth year general relativity course. They use that book. And then another one, the two I use a lot is Carroll and Wall. Sean Carroll and Robert Wall. So and then and those are the two main ones for those two.
Okay, now proceed for next question. There's three more questions here. Yeah, it's from Zhang Hao again. So is there any constraint on the multiverse? If all the constants are different in the multiverse, then all the universe is an independent event, or all the bubbles are constrained in a container? If it is, then do we able to find the container? If it isn't, then the number of bubbles are unlimited?
Yeah, I would say it depends on the specific theory of inflation. So just now in the slide, right, at least there's so many mechanisms. But in most of them, I would say that they do not provide constraints on the number of universe. Because usually the theory, right, they can write down an equation to represent the space-time, right? And then it's like variable x, and then when we put a variable x, we don't usually we don't say like what is the boundary of the interval, right? So in that sense, we do not really specify the constraint. And then universe independent constraint in the so I think the bubble is a natural container in some sense, because you have the false vacuum, right? And then at some point, there's a phase transition to the true vacuum. And then this point becomes the true vacuum. It expands as a universe according to the Friedmann equations. So that one forms, the scale factor will define a natural container for this particular universe. Then yeah, so the friend for the false vacuum essentially is almost infinite. Unless one of the theories kind of like say additional assumptions to it, but the description, or the common description is that yeah, you keep on bubbling, this one, and then if you say that, then more or less it's infinite.
Okay. So there's a question: how does the concept of the multiverse relate if our universe is infinite in size? Since in an infinite universe, any event of however minuscule probability will occur somewhere in the universe itself, and what will a different universe, assuming law of physics are consistent in universe involved, project onto each other when the universe is infinite? Will there be any difference between them?
Oh, so I think the answer to this is yeah, it's not really depends on the physics anymore, right? So if there's infinite universes, then and assuming the laws of physics are the same, then there are infinite possibilities. So almost anything can happen, right? So that's why it's being called a multiverse. So since there are so many different versions, then again you can have another version of myself that is doing a different job, right? Another version of yourself that is in a different university, and so on and so forth, right? So so I would say, yeah, simple answer is there will be just like different universe with different lives inside, and maybe there will be another universe where I'm not even born, or maybe I'm born and then I do something different, right? Or born with a different name, or having a different race or gender. Who knows?
So here's a question. Two questions. Awesome. One is, personally, what are your views on the multiverse? Do you believe in it? Second question, which of the stories you talk about is your favorite, most likely believed to be true, or personally believe?
Oh, interesting question. So do I believe in multiverse? I think I would say, yeah, just maybe probably not, right? In the sense that, this is the universe that we are stuck with, right? We can't go anywhere else, so we might as well take our own universe seriously rather than having another multiverse. But the paper about nonlinear Schrodinger equation is something interesting to consider, and probably something interesting to work on, right? Whether it's true or not. The stories I talk about, which one are my favorites? So, I mean, none in particular, but okay, just to give a concrete answer, right? The poster in the slide that I showed just now is about the movie Uncertainty. I'll just talk about it just because this is compared to Spider-Man. I think most people haven't heard about this movie. I kind of like that movie. So the story, right, is about the Joseph Gordon-Levitt, and Lily Collins, the couple. It's kind of like a multiverse story, but the idea is, the plot line, right, is that the couple was in a taxi, and then they find a phone. Someone left behind the handphone in the taxi, right? So they make a decision. Either they try to keep the phone and try to return it to the owner, or they just drop the phone, just continue going to whatever they are doing, right? So that is the story of the movie, and this decision kind of like splits into two directions. And in the movie, we follow both directions, and we get very, very different results. So yeah, so that is one of my favorite stories.
Okay, so it's a last question, I think. So I think it's maybe from your student. Okay. Will you be teaching GR for undergraduates in Xiamen University Malaysia?
Not sure yet. So probably next year. Yeah. It depends on like
Yeah, can we audit also?
yeah, sure. No problem. Yeah, but yeah, probably next year. So yeah, if you want to come, yeah, you're welcome.
Okay, sure, we will come if the course is open.
Okay.
Okay. So yeah, so any question? So any question from the floor, you can open your mic or type in the chat box, or I think open the mic. I think yeah, I think there's no question here since our time is almost up. Okay, so let's proceed to the next session. It's a photo session. Okay, so everybody can open your cam so to take a photo for this event. Don't be shy and can. So the Hong Chen will be screenshot on this. Okay.
Hello everyone. You have 2 minutes to turn on your camera, and for your information, only those who turn on their camera will be given my CST points.
Yeah, as I mentioned in the talk as a start. Okay, so okay, I think can snap.
Okay. So everyone, please do not touch your camera or your mic when I'm taking the photo because this would move the pictures. Okay, thank you everyone. You can turn off your camera now.
Okay, so yeah, so our talk, physics coffee talk today is officially end. Thanks for Dr. Lim having the talk today. So one last thing before you leave the feedback form for ESM student, the feedback form will be released now in the chat box, or you can find it by scanning the QR code from the sharing screen. The Thomas will share the screen. Yeah, so I will share the form at here. Yeah, and other university student, you can leave the feedback form. You can fill the feedback form also. So you can fill your feedback. Okay. So please be aware that the form and this meeting will be closed at 3:45 p.m. So thank you once again for your cooperation. Stay safe, and for ESN students, enjoy your 1 week mid-sem break. Thank you. Thanks, Dr. Lim.
Okay, thanks everyone. Thanks for
Thank
coming.
you for coming, Dr. Lim. Thank you. Thank you very much.
Thanks for having
Hope
me.
to see you someday. Yeah. Thank you.
Yeah. Bye bye.
Bye.